trig compound angles. So before we start looking at our compound angle rules today, the first thing we want to do is just have a little look about a relationship in our right angle triangles, because this is going to be important information in order for us to solve our proofs. So when we have a right angle triangle, if we mark in an angle theta into our triangle, we call the side opposite the opposite. We call the side opposite the 90 degrees the hypotenuse. And then the side beside the angle is called the adjacent. We already know that sine theta is equal to the opposite over the hypotenuse. And we know that cos theta is equal to the adjacent over the hypotenuse. So if we look at this triangle, if the side marked theta is added to 90 and then taken away from 180 degrees, because three angles in a triangle add up to give us 180 degrees, then we have 180 minus theta plus 90, which gives us 180 minus theta minus 90. Which is equal to 90 minus theta. So what that means then is that remaining side up here, this angle up here is 90 degrees minus theta. So if I look specifically at that angle there, 90 minus theta, then the side opposite the angle is the opposite side. Let me use purple here, is now the opposite side to the angle 90 minus theta. And if we look at the 90 degrees, well, that is still opposite the hypotenuse, so the hypotenuse hasn't changed. But then the remaining side must now be called the adjacent. In other words, what was the adjacent is now the opposite. What was the opposite is now the adjacent. So if we look at the relationships between those two angles, what I can actually say is sine theta was the opposite over the hypotenuse, but that's now the adjacent over the hypotenuse. So therefore, adjacent over hypotenuse is actually cos. And therefore, what I can say is that cos of 90 minus theta, which is the adjacent over the hypotenuse, is the same as the opposite over the hypotenuse for theta. In other words, cos 90 minus theta is the same as sine theta. Now, if you try that out on your calculator, what you'll actually see is if you get, cos 90 minus 30. Well, 90 minus 30 is going to be the same as sine 60. Or not sine 60, sorry, sine theta. Theta is 30. Apologies. In other words, cos 60 is a half and is the same as sine 30, which is also a half. So you can try that out on your calculators, okay? I'll just move that screen over a bit for a second. And of course then, if we look at what was cos theta over adjacent over hypotenuse, well, the adjacent is now the opposite over the hypotenuse for 90 degrees minus theta, which means then that sine being the opposite over hypotenuse, so for 90 minus theta, well, that's equivalent to the adjacent of the hypotenuse for theta. In other words, it's equal to cos theta. And again, you could choose any value for theta there. If I just scroll down there, you could choose any angle for theta. So say we had sine 90 minus 60 this time would be equal to cos 60. In other words, sine 30 is equal to cos 60. So again, you end up with the same thing there. But you could try in anything. You could try 10 degrees. You could try, so let's do that. Let's say sine 90 minus 10. So you're obviously going to get a decimal answer this time. Would be equivalent to cos 10. So if you go to your calculator and you put in cos 80, and then you put in, if you put in sine 80, and then you put in cos 10, what you'll find is you get exactly the same answer. And that's because of this relationship here between the right angle triangle. So really, really important is that this, let me just, if you've taken that last bit down, you can pause that. But these ones that I'm starring, they're not in your maths tables. You need to know them off by heart, okay? And that's going to be really important for our proofs. So the second thing to note is if we look at our unit circle, we know that if I draw any point on the unit circle, that we call that point out to cos of the angle. So let me draw the radius. And I'm going to say the angle traced out with respect to the x-axis is b. So that would make that coordinate cos b sine b. So remember, your x-coordinate is always cos and your y-coordinate is always sine. Now, if I drop a line down there to make a right angle triangle, and then I continue the line all the way down, and I draw it back, so that this angle here is the same. Then the coordinate here is going to be still out to cos and down to sine. However, I've now gone down in a negative direction. In other words, the x-coordinate is still positive, but the y-coordinate is negative. So in the unit circle, we always go in an anti-clockwise direction. But if I go in a clockwise direction, that's known as a negative angle. And what that basically means that if I'm getting cos of a negative angle b, then that is the same as cos of the angle. So if I go clockwise or anti-clockwise there, I will still have a positive value. Whereas if I go sine of a negative angle, well, it's negative of sine b. And again, you can try that in your calculator. You could put in sine of minus 30 and put in sine of 30, and you would see that it would be a negative answer for sine of minus b. And then, obviously, because tan is sine over cos, well, if I get tan of a negative angle, it's going to be minus sine b over cos b, which means that will also be negative for tan. And these are in your maths tables, you'd be glad to know, and that's on page 13, directly under the, directly to the right of the unit circle. So if we look, you'll see here they are. Okay. Okay, so we're ready almost to start doing our compound angle proofs. But just to highlight to you which ones we have already done in class. So we have already done one, which was our cos squared plus sine squared equals 1. We've done our sine rule and we have done our cosine rule. So today what we're going to do is 4 and 5. Now, important thing to note is up here in the right-hand corner, it states that it will be assumed that these formulae are established in the order that they are listed here. In other words, in deriving any formula, you may use the formula that precedes it. So in other words, I can use cos squared plus sine squared a equals 1 to help prove 4 or 5 or 6 or 7 or 8 or 9 or 10, because 1 has already been proved. But I would not be able to use, say, sine a plus b or sine a minus b to prove the cos of a minus b or the cos of a plus b, because they come after 4 and 5, if that makes sense to you. So you can often come back to this and refer to the ones that we have done and tick them off as we go along. So the ones that need to be proved for leaving cert is 1, 2, 3, 4, 5, 6, 7 and 9. So they're the ones that are the examinable ones. However, 8 can be derived from 7, as can 10 be derived from 9, sine 2a, cos 2a, tan 2a, cos squared a and sine squared a. So they are all kind of show the left hand side equals the right hand side, and therefore would still be really important to know. 17 to 24 would never be asked to be proved or derived or show left hand side equals right hand side. So we're going to start with theorem 4. Prove that cos of a minus b is equal to cos a cos b plus sine a sine b. So this is the long proof for all of these compound angles, and then the rest of the proofs for the compound angles are all really short because they all stem back from this one. So the first thing we're going to do is construct the unit circle. In other words, center is 0, 0, and radius is equal to 1. So if I take a point on the unit circle, I mark it in, then if I draw the line from the center to that point, that means it has radius 1. And we know our coordinates is cos followed by sine. So I'm going to call that angle that has been traced out b, which would make that coordinate cos b sine b. Now if the radius wasn't 1, it would be or cos b or sine b, whatever the radius is. I'm then going to take that point and I'm going to trace around the unit circle. So I'm going to move around the unit circle to another point along the circumference, and I'm going to do that in the second quadrant. And again, it doesn't matter where I draw that. I happen to have drawn it in the same position. It could be up here. You know, it's not relevant where I put the point. I'll just leave it there, okay? So again, if I connect from the center to that point, that's radius 1. So the angle that I've traced out from the x-axis to that point, we're going to call angle A. So that would mean that this point here that I've drawn, let me remove that yellow arrow. Well, that point will be called cos A sine A. So if I connect those 2 points, what you're now going to see is a triangle. And if I look at that triangle, and if you want, you can take the triangle out if you want to see it a little bit clearer. Or you can just mark in the angle in your unit circle, doesn't matter. What I have, get rid of those lines, is this point here, and the angle will be angle A minus angle B. I'll have lengths of sides 1 and 1, and let's just call the point here P to Q. I'm going to call that point P and that point there Q. And if you want to mark in, that'll be angle A minus B. Okay, so now I've got my construction done. What we're going to do is we're now going to try and prove that cos of A minus B is equal to cos A cos B plus sine A sine B. And to do that, what we're going to do is we're going to get the length of the side PQ in 2 different ways. So we're going to use the distance formula first. And the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. And again, that's page 18 in your maths tables if you can't remember that formula. And we're finding the length of the side PQ. So if I go up to PQ there, it doesn't matter which one I call x1, y1 or which one I call x2, y2. It makes no difference. So it's going to be the square root of x2, which is cos b minus x2 minus x1, so cos a, and then I square it, plus y2 minus y1 to be squared. So I want to get rid of that square root sign straight away, so I'm going to square both sides. So if I square the left, I get PQ squared is equal to cos b minus cos a squared plus sin b minus sin a squared. Okay, so let's square the right-hand side. So if I square the right-hand side, I get cos squared b, multiply them and double it, so that's going to be 2 cos a cos b, or cos b cos a, doesn't matter which way we write it. But I know if I go back up here, it's written as cos a cos b on the right-hand side. So I'm just going to say cos a cos b, and then minus cos a squared, well, that's going to be minus by minus, which becomes plus cos squared a. Now if I square out the sin b minus sin a, well, square the first is sin squared b, multiply them and double it, so minus 2 sin a sin b. I'm just going to move the screen across here, and then we have minus sin a by minus sin a is going to become plus sin squared a. Okay, so what you should notice, hopefully, is that we have a cos squared a and a sin squared a cos squared b and a sin squared b. So I'm going to group those two together and see, can you spot anything? So if I group the sin squared a and the cos squared a together, and then I group the sin squared b and the cos squared b, and then the other thing I notice that's common is that we have a 2 in front of this cos a, cos b, and sin a, sin b. So I'm going to take out 2 as being the highest common factor there, and it's minus 2. So again, I'll just move the screen over. So if I take out minus 2 as being common, that leaves me with cos a, cos b, plus sin a, sin b. And now it's like, ooh, hang on a second. If we look at the top there, cos A, cos B, sin A, sin B. So I actually have the cos A, cos B, sin A, sin B that I'm looking for. But I don't want all of this. But if you go to page 13 in your maths tables, or even if you went back to the previous page, the most commonly used identity is this first one here, and it says I can use anything that has been proved before theorem 4. So cos squared a plus sin squared a is equal to 1. So therefore sin squared a plus cos squared a is the same as cos squared a plus sin squared a. So that means that that first bracket is 1. The second bracket is also 1. And therefore that's going to be 2. Minus 2 times cos A, cos B, plus sin A, sin B. So we're going to call that equation 1. So the second way in which we're going to get PQ is to use our cosine rule. And our cosine rule is a squared is equal to b squared plus c squared minus 2bc cos A. And again, if we can't remember that, that's page 16 in our maths tables. But if we go back here, and again, you can see I took out that triangle from the unit circle for the purpose of the cosine rule, because A minus B, well, the side opposite is PQ. So if I was looking at my cosine rule, that's like saying the side A and the angle A and the side B and the side C. So in other words, if I'm putting them into the cosine rule, instead of A squared, I'm going to put in PQ squared. Instead of B squared, I'm going to put in 1 squared. Instead of C squared, I'm going to put in 1 squared. And instead of cos A, I'm going to put in the angle A minus B. So therefore, this formula here is going to become PQ squared is equal to 1 squared plus 1 squared minus 2 times 1 times 1 times cos of A minus B. So therefore, PQ squared is 1 plus 1, which is 2, minus 2 cos of A minus B. And now this is getting really exciting because that's almost the left-hand side of what it is I'm trying to prove. If we go back, zoom out here, you can see I'm trying to get cos of A minus B is equal to cos A cos B plus sin A sin B. So what we're going to do next is we've just gotten PQ squared for 1, and we've also gotten PQ squared equation 2. So of course you can guess what's going to happen next. We're going to equate 1 and 2. So I'm going to put the one with the cos A minus B on the left-hand side because that's what we're trying to prove, okay? Doesn't matter which way we would write it, because left is equal to right and right is equal to left. They're both equal to PQ squared. So 2 minus 2 cos A minus B is equal to 2 minus 2 times cos A cos B plus sin A sin B. Okay, and you can see obviously we have a 2 on the left and the right, so 2 minus 2 is 0, and that leaves me with minus 2 cos A minus B is equal to minus 2 times cos A cos B plus sin A sin B. And of course, I can now divide both sides by minus 2, and we've gotten our answer. Cos of A minus B is equal to cos A cos B plus sin A sin B. So we say QED. So theorem 5 is a hell of a lot shorter. It's literally 3 lines. And we're going to try and prove that cos of A plus B, this time, as opposed to A minus B, is equal to cos A cos B minus sin A sin B. Now, if you go back to the previous proof, we proved that cos of A minus B was equal to cos A cos B plus sin A sin B. So what you should notice is that the only difference here is the minus, and the plus has now become a plus and a minus. So the signs have literally just swapped here in this answer. So that's kind of the hint. When the sign is the only thing that has changed, then what we're going to do is we're going to start with what we've already proved, because we know that we can use the previous 4 proofs here, but we cannot use anything after. So we know that cos of A minus B is equal to cos A cos B plus sin A sin B. So you don't have to prove that all over again. It is assumed to have been proven true now at this stage. And all we do is we say, well, let the angle B equal the negative angle B. So wherever there's a B, I'm now going to replace that with minus B. So we have cos A minus, and instead of B, I'm now putting a minus B, is equal to cos A cos, and instead of B, I'm putting minus B, plus sin A sin, and instead of B, I'm putting minus B. Now what that does to the left-hand side is straight away it gives me A minus minus B, which is A plus B. That was easy. And on the right-hand side, well, this is one of the first things that I was showing you here in note 2. It was the cos of the negative angle B and sine of the negative angle B. And I also told you that was the handy one because it's page 13 in your maths tables. And if we look again on page 13 in the maths tables, we can see that if we have cos of a negative angle, it's the same as cos of the positive angle. So that means that cos of minus b is just going to stay as cos b. But sine of minus b is going to become minus sine of the angle. So that's plus sine a, and please make sure here for this bit that you use brackets, because otherwise it ends up looking like you are subtracting, but you're not subtracting, you are multiplying. And now I have my answer, because it's cos a plus b is equal to cos a cos b, and sine a times minus sine b is a negative answer. So it's minus sine a sine b, and you're done. And 4 lines, I should say. I think I said it was a 3-line proof at the start. Didn't quite lie. Okay, so second one, obviously really nice. First proof, a little bit longer, but it's the cosine rule and the distance formula rule for the proof. So no calculations today, as I said to you yesterday in our meeting, literally just learning your proofs.